Hello, and thank you for joining me. You're here with Data Science Teacher Brandyn, and we're going to be going over the deep learning tips for how to build a convolutional neural network with the functional API. So we can do some fun things with this. We're just going to use, well, not just the MNIST. I think this is the Kanji MNIST dataset. So we're going to use characters here. This is Japanese characters. You can see, well, maybe not so easy to see, but we can see MNIST, again, so just from 0 to 9, 0 to, again, digits, but in the Japanese alphabet, I guess, with Japanese characters. So just to do something a little bit different, nothing really super fun there, just loading it from the TensorFlow dataset. An important thing that to understand about this is these are now tensors, not a NumPy array or pandas data frame, which affects something later on that we'll see. So just understand that the data type here is a tensor, not an array or a data frame or a series. Okay, so going through that, what I'm doing here is I'm building, to make my coding down here a little bit cleaner, I'm going to build a convolutional block, and usually you do two convolutional layers side by side, followed by a max pooling, and then typically a dropout layer. I had here the option to turn it off as well, but it's typically you would do convolution, then followed by a dense layer for every block. Okay, so what I'm doing here is I'm doing convolutional layers, and I'm just going from the layers, which came from the TensorFlow library here, from tensorflow.keras import layers. Okay. Just to make coding a little bit easier, to cov two-dimensional filters, kernel, activation prelude. So I have the big thing in here is this X, this first position right here. This is going to be the output from the layer above, or in the first block, it will be my input layer right here. So I'm just going to take that and multiply it by it. Not really multiplication, it means the function is going to be happening inside. It's a weird syntax of Python that allows this, but you can kind of think of it multiplied by. Okay? And so we're going to multiply by the inputs or the layer above, and we're going to bring it in here, and then it's going to go into the convolution, another convolution, filters. So filters are the number of planes. You can kind of think of them like neurons, although they're really the two-dimension or three dimensions of images, depending on how many channels you have, but really our two-dimension are X and Y, but it's going to be 16 of those. And each one of those filters, kind of like a neuron that captures a pattern here, but specifically we're capturing a higher level pattern in that we're getting shapes, lines, and stuff like that. And then my dense neurons is just 44 to start. Okay, so going to that, and I'm making the option to include or not include the dropout, although normally you would want to include the dropout. We're returning the output of the dense layer that follows the stream down. Okay. So start with this, you have to define your input layer separately. So layers.input. My shape is 28, just like the regular MNIST. However, we're doing the KMNIST today, and I'm going to do one call block. I'm putting the input into this. The first layer, the layer above, is going to go into my function and then not multiplied by, but passing to the call to the block. Okay. And then doing another one with 32 filters, then 16 filters, and then I'm doing flattening. So I'm doing the flattening outside of these convolutions. I want to do the convolutions, these two sets of blocks, and then flatten. Then a dense layer, and then you could have done the flatten layer inside of this function if you weren't going to do two blocks, and you could do 3, 4 now, and then flatten it afterwards. Okay, so it gives you that flexibility. Okay, and then again multiplying by the layer above it, and then the same thing goes down, and we do the MNIST here. So this is in its essence very similar to a sequential model, just straightforward, showing that example first. And the way that we're going to define our model is tf.keras.models.model inputs, and this is a dictionary that's attaching to the name that I gave my input layer and what the layer is going to be. And then outputs is attaching to the output layer right here, which is just a dense layer with 10 neurons. And an output layer. Sparse categorical cross entropy because it's one column of data. And so that's the sparse is one column of data, a lot less data than if I were to one-hot encode this and have each column have its own, each class in our target 0, 1, 2, 3 have its own column in the predictions. That is what we'll get out in the 10 neurons here. But to give it just a one column set of data, we're going to give it the sparse categorical cross entropy, doing the atom optimizer, which is generally good all around one, and I'm going to ask for the accuracy as well. tf.keras.utils.plot underscore model, and putting the model in there to take a look at it. And again, it's exactly the same as you would see in sequential model. Train, so model.fit, train, kind of right at this point, it's very similar to what we would see in, because we only have one input and one output, very similar to what we see in the sequential. I'm going to use the Plotly version of Pandas data frame, or have Pandas engine be using the Plotly, so that I can get a lot of detail on the training history and just see exactly what the value is. Pretty easy to see, but if you wanted more detail, if it was longer, I only trained it for 10 epochs, but if you wanted to do it for longer, it can be very helpful if you train it for like 100 and really see what level, what the numbers are. Okay. Doing a confusion matrix here to really see our predictions, and you see train, we do quite well, and 97% F1 score overall. Our accuracy is 95%. And this is just printing out the classification report at the very end. And I'm taking the argmax of the predictions to put this in, and the argmax of my predictions in the confusion matrix, because what comes out is 10 columns, one for each class. Okay, so we're taking the maximum across the rows acts as 1 to get their final prediction. And then the same thing here as well for the test. Not quite as good on the test. We got an 86% on the test, or a score of 86, an accuracy of 86. Okay, to have a little bit more fun with this, I'm going to do something that we could only do with the convolutional layer. I'm going to be defining two inputs here. Okay, so input, and then we have input 2, convolutional block 1, convolutional block, and this is all for the first input, and then convolutional 2 connects to this second input right here. Okay, so convolutional 1, or sorry, second convolutional block. So basically what's happening is that each picture, we're going to have two inputs here, and each one's going to go through its own convolutional block before connecting and flattening, and then concatenating, dense layer, and then output. Okay. So we do each convolutional block for each side, and then flattening both sides, concat right here, layers.concat, and then the dense layer, and then the outputs. And that should be a flat layer right there. Okay. Oh, sorry. I apologize. I did the flat layer above. That for you guys. I just to highlight what I did here, I did it afterwards, but I couldn't concat the two layers here. I thought I would do it, just I wasn't thinking when the first time I did this. I did it afterwards because it just made sense when I was thinking through, but really you can't, because they're going to be different shapes. I'm going to be putting, as you can see, different kernels, and so it's going to make the output different shapes. So you can't concat them until they've both been flattened and they become the same shape. So a little small minor thing, but just to make sure that you're flattening these before you would concat two convolutional outputs. And then in the inputs, I'm going to be defining a dictionary for the name of the one, and then input, the name of the second one, and then input right there, and then a dictionary to define the output, connecting the name to the output of the layer. Same loss, everything else is the same in the compile. Looking at the plot model here, we can see we do quite well, or quite interesting looking model. When I'm doing the fit, just to highlight this, I had to do train.numpy. The reason being is because it's a tensor, and so tensors keep track of TensorFlow is keeping track of everything as it's going through a model. I had to kind of disconnect it from that because I'm going to be using the same input in both of these, just a different kernel, but the same image is going in both sides. So I'm just turning it into a NumPy array here to disconnect it from the tensor. Nothing really changes in this sense, but just to disconnect it, right? Because I'm using the same input in both sides. Very minor, but a data type issue, right? We always have to pay attention to our data types. Saving the output to H, plotting the history. I apologize, I forgot to do the test set here because I just forgot, and it took a while to train this one, so I wasn't able to do it again before I made this video. And you can see here the same thing for the train test. The way you're doing the predictions is you're passing it to the dictionary. Okay, input K1, train numpy, input kmnist2, and then the train. Okay, so you're doing this, and then I'm selecting the outputs from this to make sure that what I get, because you get a dictionary with each output attached to key and value pair in the dictionary, and so you just have to pull it out of the dictionary that's produced and just get the actual output and do the predictions. And again, we're doing argmax across the axis 1, doing the output here across the rows. And you can see 97%, a little bit of improvement on the train, but we don't really care about the train, right? We care about the test. And so here in the test, you can see that we get a significant, I'm doing the exact same thing in the predictions, but you can see we got a 93%. So we didn't change anything, no new data, nothing really changed in there, but we did two different convolutions, the same convolutions, but different kernel size. And you can think some are capturing the bigger pictures, bigger shapes, and some are capturing more little small details. And then together, that's able to define, especially in our Japanese characters right here, where there's lots of small, unlike MNIST, there's lots of small little details, but there's also the bigger, grander thing that's going on. So we need to understand kind of both of those to get good prediction. A little bit trickier than the regular MNIST data set for sure. Okay, so thank you very much for joining me, and I will see you next time.